Hi, my name is Caroline Brown, and I'm a third-year biomedical engineering student here at Georgia Tech. I'm taking Physics 2 with Greco. I attended the public lecture given by three Georgia Tech professors about the three Nobel Prize winners for physics in 2018. These physicists were awarded Nobel Prizes for their groundbreaking inventions in the field of laser physics. It was very interesting to see what was going on behind the scenes at Georgia Tech and what was going on in all of the labs that the faculty were involved in. The first professor discussed the Nobel Prize that was awarded to Gerard Mourou and Donna Strickland for their method of generating high-intensity, ultra-short optical pulses. The first topic discussed was ultrafast optics. They proposed the galloping horse controversy and had us talk about it as a whole lecture hall. They talked about how to generate short pulses and how high intensity can turn a medium into a lens. They provided us with a graph of the light-electric field versus time graph and discussed how it typically goes through a rainbow of colors, with going from red to violet. On this graph, high intensity would be a white color. The technique that this professor was studying in his lab at Georgia Tech was known as frequency-resolved optical gating, or FROG. He showed us the setup of this device and this technique that he currently has at his lab at Georgia Tech. There's competitions to this technique, and one competition to this technique is SPIDER. With this technique, we can measure pulses in time and space. There's also coherent control, so we use ultra-short pulses to control a chemical reaction. He also discussed two-photon imaging. The next professor still discussed Gerard Mourou and Donna Strickland's half of the Nobel Prize for 2018 physics. He focused on how light is a wave. He discussed what waves have in common, and that is that they oscillate back and forth. Light waves, the E field is oscillating. There are different frequencies of oscillation for different light waves. For example, red has low frequency and blue has high frequency. Additionally, the force of light wave is much weaker than interatomic forces. He also discussed laser cooling. The professor cools atoms with lasers at his lab at Georgia Tech. He discussed chirped pulse amplification, which involves stretching the pulse before amplifying it and then compressing it later on. He discussed how the stretching was achieved and talked about how light at different frequencies travel at the same speed. Applications of this chirped pulse amplification include physical chemistry applications, applications in high-energy physics, X-rays, and in clinical settings such as laser eye surgeries. The last professor discussed optical trapping. This was discussing the half of the Nobel Prize that was awarded to Arthur Ashkin for the optical tweezers and their applications to biomedical systems, or biological systems. He discussed Arthur Ashkin was interested in moving objects with radiation pressure. The idea that light can move objects is not new, but he did study how momentum is conserved, how light carries momentum, how light's momentum is related to the direction light is traveling. So when light is reflected or refracted, its momentum changes. He then is using optical tweezers to trap particles and move particles. Those are the main points that was addressed in this public lecture. So what I learned, I didn't really know a lot about the field of laser physics going into the public lecture, so a lot of this is new information for me. Some of the many things I learned include that force of a light wave is much weaker than interatomic forces. High-intensity lasers can turn a medium into a lens, and how chirped pulse amplification works and its useful applications in physics, chemistry, and medicine. One of the things I did not know before coming into this lecture, or one of the things I did know, is that the frequency of oscillations of light waves are different for different colors. For example, red is low frequency, blue is high frequency. That I didn't know before going in. Something that sparked my curiosity in this public lecture is that they said Nobel Prizes are often hiding in plain sight. All it takes is for the right person to find them. That's really interesting because as long as you can find them, then you're golden. So after this public lecture, I followed up with this topic by researching more into the Nobel Prize winners for this year and their accomplishments. I looked at optical tweezers because I was interested in that topic and I didn't understand fully how it worked. And I learned it's a technique for trapping, transporting, and patterning of metallic nanoparticles. Um, they're going to hold and move microscopic objects similar to normal tweezers. I thought all of this was really interesting, and while none of it directly related to anything I had learned in a biomedical engineering course so far at Georgia Tech, I would definitely keep it in mind moving forward.